Our next topic is we're going to take a peek at what are known as resonance structures and molecular structures. For resonance to even be possible, the molecule must have one or more pi bonds as part of its structure. Let's use benzene as an example for how resonance structures are possible. Now, one person might draw benzene with its characteristic single double single double single double alternating bond sequence in a circle, as we see here. Whereas we could also represent the structure as shown on the right, where the location of our single and double bonds has been offset by one position in the structure. Using Lewis structures, this is the best we can represent the benzene molecule. The reality is, with what we've been able to observe with benzene, is that benzene is actually, in a way, an average of these two structures. And it's largely due to the fact that the pi bond electrons from the double bonds, the second bond in our double bonds, those electrons are not trapped between the nuclei. Because the pi bond electrons are not trapped between the nuclei, those electrons are able to drift from one carbon atom to the other carbon atom. The overall effect of this electrons being able to move throughout the benzene ring is that all the bonds in the structure end up becoming equivalent to one another. Because what occurs is that the pi bond electrons end up being evenly distributed amongst all the bonds in the structure. An observer looking at a benzene ring doesn't see any double bonds nor any single bonds in the structure. The structure does not actually show any double or single bonds. So what we represent here is not the actual structure of a benzene. What the observer would really see is that all of the bonds between the carbon atoms are actually 3/2 bonds, directly between the size of a single bond and a double bond. It's an average of all the bonds, creating essentially a bond that is 1.5 bonds. A 1.5 bond is observed to be directly between the length and strength of single and double bonds. It's right between a single and double bond. Essentially, we have a 1.5 bond between all of the carbon atoms. The way we represent this phenomena of these bonds averaging together is something known as resonance structures. In resonance structures, the two possible Lewis structures are both drawn, an arrow is drawn between them, and brackets are placed outside both of the structures. What this communicates is that the structure is really neither one structure nor the other, but it's actually an averaging or blending of the two structures together. Just as we have limitations in our depicting of them with Lewis structures, where we can't show exactly what they look like, so we draw the best we can and then represent this as saying that this is an average of the two structures that we've drawn. Now, any structure that has a pi bond has the possibilities of resonance. Let's take a look at NO2 the nitrite ion. One Lewis structure of nitrite looks like this. Double bond oxygen to the left, a single bond oxygen to the right. A second Lewis structure is as shown on the right, with the double bond oxygen now going to the right in the molecule. The placement of the pi bond's been moved. The reality is that nitrite is a blending of these two. This would be our two resonance structures that we have for the nitrite ion. And we don't actually observe any double or single bonds in a nitrite ion, but rather the observed bond size is directly between the two. We again see between the oxygen and nitrogen atoms a 3/2 bond. Our 3/2 bond comes from, we have three bonds that are split between two bonding locations. Let's do one more quick example. Let's look at nitrate, NO3 The nitrate molecule has several different resonance forms. There's 3 different ways we can depict this with the Lewis structure. If an observer were to look at a nitrate ion, they would not observe any single nor double bonds in this particular structure. But rather what would be observed is that all the bonds are equivalent and each bond would be a 4/3 bond, with each bond between the nitrogen and oxygen being exactly the same size in length and strength. The 4/3 bond comes from, we have 4 bonds split between 3 bonding locations. So the bonding electrons get averaged out and evenly distributed between all the bonding locations. In drawing what are known as resonance structures, there's a couple guidelines to follow. The atoms retain their location in the structure. As we look at these resonance structures for our nitrate ion, the oxygen, nitrogen, and oxygen atoms in each structure have not been moved. They retain their location in each of the resonance structures. A second guideline is that it's only the pi bond or bonds that change location in drawing one resonance structure compared to another resonance structure compared to another resonance structure to represent what's taking place in the structure of this particular molecule or ion.